So triple integrals, well, it's one more integral than what we did last time on double integrals. So we already looked at what finding the double integral really means. So again, when we have a double integral in a domain D or R, well, when there's an invisible one in the integrand, that integral represents area over the region D. All right, and well, oh yes, and when we have a double integral with some f of x, y, it could be dy dx or dx y, depending on how do we define the integral, depending on which one is easier, if it's vertically simple or horizontally simple, or if it's either or if it's both vertically and horizontally simple. It's either way. All right, that integral represents volume. So today we're going to look at triple integrals. How do we compute them? Well, the domain x going from a to b, y goes as a function of x, and z goes as a function of x, y. And we are integrating some f of x, y, z. Alright, so let's do one example. Later we will discuss what this really represents. Alright, so let's evaluate the triple integral of x, y, z cubed squared of dv with respect v over the region B, where the region B is defined from x going from 0 to 1, y goes from -1 to 2, and z goes from 0 and 3. So in this case, this is like, you know, the straightforward type of integral, and in this case it really doesn't matter which order we go, but typically we go in the backwards alphabetic order. We do dz, then dy, and then dx, but it really doesn't matter much. All right, so let's set up the triple integral, and that's x. I'm leaving some space for the limits. X, y, z squared, and well, we can go about dz, dy, dx, and in this case we can go in our favorite order, because look at the limits of integration for each direction, x, y, and z. They're all constants. However, if we had, you know, variable limits of integration, well, we would have to look at the representation, or rather the projection of the region in the xy plane, and determining whether that projection is horizontally simple or vertically simple, to go about the easiest way. And even if we go about the easiest way, we could run into a situation in which the integral may not be integrable with the methods that we know so far. All right, so in those cases, despite we choose the easy region, there's no way around that integral with the methods that we know. But in this case, well, these limits are really nice. They're constant limits, so let's just go. The limits with respect to z, that's from 0 to 3. The limits with respect to y, that's from -1 to 2. And the limits with respect z in this, or rather x, which is from 0 to 1. All right. So let's just go about the integration. So in this case, we're going to integrate with respect to z. That's going to leave us with the double integral from 0 to 1 and from -1 to 2 of the integral of x, y, z squared with respect to z. So in this case, we're integrating with respect to z. X and y are constants, are like 5z squared, 7z squared. So that's just x, y, z cubed over 3 evaluated from 0 to 3. And don't forget the dy dx. And as usual, fundamental theorem of calculus. So that's the double integral from 0 to 1 and from -1 to 2 x, y, and in this case recall that we are evaluating the integral only with respect to z. So these limits of integration are going to be plugged in are going to be plugged in the variable that we are integrating with respect to, in this case, z. So x and y just remain there. So that's going to be, so that's over 3, and that's 3 squared minus 0 squared dy dx. All right. And well, what else do we have? Well, let's simplify this. So that's 3 squared, which is 9 over 3. Isn't that a 9? Oh, wait a minute. No, that's cubed, right? That's 27. Yes, that's 20 because I was looking at my notes. So that's 27 over 3. That's a 9. And integral from 1 or negative 1 to 2. And that's 9xy dy dx. So it's time to integrate with respect to y. Well, take the 9 and the x as constants, integrate y. So that's going to leave us with the integral from 0 to 1 of 9xy over 2, that y squared, and that goes from negative 1 to 2. And don't forget our dx. And again, fundamental theorem of calculus, but in this case with respect to y. And again, because we integrated with respect to y, these limits should only be plugged in the y variable, leave the x alone. So that's the integral from 0 to 1, and that's a 9x over 2, and that's 2 squared minus negative 1 squared dx. So that's going to be 2 squared, which is 4, minus negative 1 squared, which is plus 1. So is that a 3? And well, 3 times 9, that's a 27 over 2. So that'll leave us with the integral from 0 to 1 of 27x over 2 dx. And well, so let's take the 27 halves outside of the integral x dx and just integrate x. So that's 27 over 2 x squared over 2 from 0 to 1. That's 27 fourths. And well, that's 1 squared minus 0 squared. That's simply, well, 1 squared, which is 1, minus 0 squared, which is 0. That's just 1. 27 fourths. It's the value of this integral. All right. I mean, it's the same rules of integration. It's the same process, doing one integral at a time. It's just that this time we're going to do it 3 times for one process, right? For this process. All right, let's have a look at another example. Number 2. Evaluate this triple integral from 0 to 9, 0 to y over 3, and 0 to the square root of y squared minus x squared of z dz dx dy. Notice the order in this class. Notice the order. So, and I know in this case, well, you look at all these limits. What are we essentially finding? Well, let's see the region we're integrating over. So number 1. So in this case, well, these limits of integration are telling us that y varies between 0 and 9. All right, that is going to be in the xy plane projection from between 0 and 9. And then the second integral is telling us that x is varying between 0 and y over 3. But this might be a little weird to see, so if we set x equals y over 3, this is the same as saying y equals to 3x. So which is going to be this diagonal line in here. Let me do this one right here, all right? So this is what's going on in the 2D region. So if we had this solid, well, that third integral is telling us that z is varying from 0, which is really the xy plane, the very bottom, or rather not the very bottom, the floor, if you will, and the ceiling or the roof will be, in this case, that radical function. All right. So in this case, well, let's write down the integral. Let's evaluate this integral. So we have the triple integral from 0 to 9, from 0 to y over 3, and we can integrate z with respect to z. That's just z squared over 2 from 0 to the square root of y squared minus 9x squared. And don't forget the dx, dy. Notice the order this time, all right? Notice the order. So, let's see. So, using the fundamental theorem again, well, so I think, let me see if it fits here, from 0 to 9, from 0 to y over 3, and that's a 1/2, and no, that's not going to be enough space. Let me move it here. So that's the quantity z in this case, which is the radical squared and minus the lower limit squared, which is simply 0 squared, dx dy. So the good thing here is this radical gets cancelled with this exponent. So yeah, that's going to give us an easier integral to work with instead of having to work on a u substitution, you know. So that's going to leave us with the integral from 0 to 9, the integral from 0 to y over 3. That's 1/2 y squared minus 9x squared dx dy. So that's the integral here. Nope. Perfect. All right. So let's integrate this in this expression that we have with respect x this time. So that means we are going to hold y squared a constant, and well, x squared, well, that's going to be whatever that integral is. However, I think it would be better to distribute the 1/2 and not leave that 1/2 out, just outside. 0 to 9, 0 to y over 3, and that's y squared over 2 minus 9/2 x squared, and let's integrate with respect x. So integrating with respect x, the integral of y squared over 2, well, that's constant with respect x. So a constant times, well, the integral dx, well, that's the constant times x. So that's y squared over 2 times x minus the integral of, well, minus 9/2 integral of x squared, which is x cubed over 3 dy, and the limits of integration are 0 to y over 3. And the original limits for the first integral go from 0 to 9. All right. So again, notice we integrated with respect x. So these limits of integration, 0 and y over 3, should go only wherever you see the letter x. And well, I don't want to substitute that y over 3 in the second term yet. I'd rather simplify these coefficients, and that's so we don't get these crazy looking fractions from 0 to 9. That's well, let me do y squared over 2 still times x. I will replace that in its due time. Well, 9 over 3, that's going to reduce to 3 in the numerator. 3 over 2, it's going to be the coefficient there. And so 3 over 2, yeah, so minus 3/2 x cubed from 0 to y over 3 dx. Again, these limits only go here whatever you see dx because we integrated with respect to x. And well, so that's going to be okay, I have something weird in here. Okay, no, that's fine. So that's the integral from 0 to 9. No, that's not going to be enough space. I'm going to go here, 0 to 9. So that's going to be y squared over 2 times the quantity y over 3, which is applying the fundamental theorem on the first term, and then minus 3 halves of quantity. Okay, so this is y over 3 cubed. All right. And so we're going to cube both the numerator and the denominator and then integrate with respect to y in the end. Oh, okay. The lower limit is 0. So do we agree that when we plug in the lower limit 0 here and in the first and the second term, that's just going to get zeroed out? So just a big 0 is fine. All right. And looks like I did a silly mistake. Okay, that's fine. So dy. So that's going to reduce from 0 to 9, integral from 0 to 9, so that's y cubed over 6 minus, oh, okay, so this is going to be 3 halves, y cubed over 27, and dy. Let's reduce the 3 over 27, well, that's going to be 3 over 9, I think, right here. So that's 1, that's 9, and then 9 times 2. That should be the integral from 0 to 9, y cubed over 6 minus y cubed over 9. And so we need to combine these like terms. So y over, so 1/6 minus 1/9. Let me do that on the side instead of just using integral. So 1 over 6.
Did you forget to multiply the 2 for the 18?
Which one? Here? Oh, oh yeah, that's 18. That's true. 18. Thank you. So 18. And so 1/6 and 1/18, or in 1 over 18. So what about 3 times 3? So 3 minus 1, that's a 2 over 18, which is 1/9. All right. So that's the integral from 0 to 9 of y cubed over 9, or, well, dy. We can take out the 1/9. And the integral of y cubed dy will be 1 over 9, first of all, times y to the 4th power over 4 from 0 to 9. But that's going to be y to the 4 over 36. And that goes from 0 to 9. All right? This look like a... All right. And as usual, upper limit. Okay, now let me take the 1 over 36. 9 to the 4th minus 0 to the 4th. So 9 to the 4, which is a big number, over that times 36, that should leave us with 729 over 4. All right. Okay. So just briefly, what does the triple integral represent again? So at the beginning of this section, we did some mini review of what double integrals represent, well, in the situation in which the integral, or the integrand rather, it's an invisible one, that's area, but when we have some f of x, and that function f of x, it's actually like the height of the solid of the area, of the solid of the region that we are finding in this case by double integration. Now, one of the applications of triple integrals is to find volume, but in this case, so if we see a triple integral in a similar way that we did for the double integral, if that integrand is an invisible one, notice in this case, this integral, this form doesn't have any f of x, y, z. It only has an invisible one. Well, that triple integral will describe, in this case, volume. However, what if we have that f of x, y, z in this case? Well, that's the very end of the section. Let's talk about it briefly. Oh, I don't think I have the updated PDF file, so let me write it down instead. So in this case, when we have the triple integral over the region D, but in this case we have some f of x, y, and z, as we're going to see later with respect v or dv for the volume. Well, there's something we may have seen before. What is that going to give us in this case? Well, so the double integral with an f of x, y gave us the volume. The triple integral with a 1 in the integrand gives us the volume again, because that's essentially, like when we compute the integral, let's say only the innermost integral varies from f to g. So that's going to be whatever that is. Let me do the triple integral, f and g, and d, z, dy, dx. So this will be, well, if we do the first integral, that's going to be z, dy, dx. And in this case, that z is basically g minus f, dy, dx, or we can call this our dA. And what is this g minus f? That's just another function, isn't it? Which is the function f of x, y that we integrated to get the volume, right? So that's how this triple integral gets related with the double integral. So we can create an identity, if we will. So we can say that the triple integral with a 1 in the integrand dv, it's exactly the same as saying the double integral f of x, y dA. Alright, so two ways to say the same thing, but depending on the information that we're given, sometimes we're given an f of x, y. That means we're integrating over a superficial region, over a 2D region. But if in this case they're giving us a really big region, d in this case, so we have to evaluate a triple integral with a 1 in the integrand. Now, what about the triple integral containing not something other than just 1 in the integrand? Well, so if we had this triple integral without the function f of x, y, that'll be just the volume again. But at that volume being multiplied by something else, what is that? So what would be that something else? Well, so you might recall this formula from chemistry. Density equals mass over volume. If we solve for m, the mass, that's density times volume. So this volume being multiplied by this function actually represents the density of the solid that we are going to find. And in this case, really this triple integral that contains an f of x, y, z, which is something other than just 1, that's going to give us the mass of the solid. And that f of x, y, z will represent the density function in this case, because if you look at the solid, for example, a solid rock. So, I mean, when we're in chemistry, we're assuming that the volume of our planet is uniformly the same material. So we just say, oh, the density is that and the mass is that. Well, that's going to be the volume, right? But if you think about more realistically, well, even a solid rock has a different density at different points, and that's described by the function f of x, y, z. All right? And actually, we already did something like this back in calculus too. You might remember the 1D version, really. When we had the mass equals the integral from a to b of the function rho of x dx. So what we were really doing is finding the linear density, which is kind of weird because we were finding the mass of that wire of length between A and B, but even still, that little wire which is described by this linear density, if you think about it, it's still solid, right? Despite how thin this wire is, or this string, it's still solid, but we approximated to just a one-dimension density. That's something we covered back in calculus, in Calc 2. All right? However, I think I'd rather get into finding volume for